Okay, now. Yeah. Not necessary. Okay, it's fine. Okay. So it's connect, right? So we will make it. Yes. Can you hear me?
Yeah, I can hear you. I can hear you.
We are now.
Yeah, it's just fluctuating. Sometimes the noise we can't hear. Yeah. The low bandwidth. Now it's a little bit bridge. The network bandwidth is a little bit low.
I think it will be okay. Hello.
Yeah, now I can see you clearly.
Yeah.
Very good image.
Yeah, you can because sorry for the presenter. There is a reason that we have a very new building, and this is also my room is here nearby.
No, that's fine.
So
It's excellent. Yeah, no worries.
the reason is there is some inspection is going on in the building that maybe
Yeah, for
next week.
obvious reason, we understand. Yeah, that's fine.
Okay, thank you so much, please. So for waiting and other who are waited, so please.
Yeah, so from the previous one, can we just call the last one for today? Then we'll call the previous one.
Yes. I mean, shortcut will be last one after this.
Okay, so I would like to now invite for PID 2025353 performance analysis of semi-supervised frameworks for polyp segmentation. Will be presented by Tarek Bashir Ovi, Fayaz Hassanuzzaman Rhythm, Numaya Bashri, MD Abdul Wahid, and Hussein Naim. So please proceed. Thank you.
Hello, sir. Am I audible?
Yes.
I'm Numaya Bashri. I will presenting this paper.
Yes, Numaya, you can start.
Sir, my screen is visible?
Yes.
Thank you, respected chair and presented all. Good afternoon. I'm Numaya Bashri. I will present this paper. So before starting my presentation, I want to talk about some important insights that what is colorectal cancer and what are the polyps. Colorectal cancer is the third most common cancer worldwide, and its prognosis is critically linked to early detection and removal of lesions called polyps. The primary detection method is colonoscopy, which relies on manual inspection by physicians, a process that is often time-consuming. So, there are some screening processes manually and the colonoscopy process. These are really time consuming. So there are some limitations like the human factors in colonoscopy lead to 20 to 30% polyp miss rate. To address this, we use computer-aided diagnosis system providing real-time, consistent, and vertigo-free analysis. So ultimately improve patient outcomes. Then we can see that there are some traditional supervised learning methods which require thousands of level images, pixel-wise annotation by medical experts, and 15 to 20 minutes per image. And these are also uh, very costly system. So to address this problem, our solution is semi-supervised learning, which efficiently leverage the abundance of unlabeled chronoscopy data alongside a small fraction of labeled data. The critical need for polyp detection are disease burden, detection challenges, economic impact. Urgent need for automated, reliable detection systems. So there is a good news. We can use deep learning with the semi-supervised learning to overcome these limitations. Semi-supervised learning are based on min-max similarity, dual segment, and deep co-training approaches. And there are some limitations for high annotated data and limited annotation cost. So we address these challenges through the extensive performance analysis of semi-supervised models within semi-supervised frameworks. I'm Nomabashi will present this paper on performance analysis of semi-supervised frameworks for polyp segmentation. This is our team, and we all from MIST, Dhaka, and Bangladesh. This is our paper ID. So the presentation outline is shown here. There are some questions in our mind that how to establish supervised segmentation models for perform when integrated to semi-supervised learning frameworks, which models, framework combinations achieve optimal performance under limited level data conditions and such on. So to address these questions, I will say that the core of our research involved a systematic evaluation of 3 semi-supervised frameworks and 9 different segmentation models to identify the best combinations for reliable, low annotation, cost-efficient polyp segmentation. So our objective is to comprehensive evaluation, performance benchmarking, framework model compatibility, and clinical applicability. These are the best output expected from our work under the clinical impact and the research impact. So certainly we are not the first, and there are many prominent segmentation models which are very good in segmentation. We utilize them in our analysis to see the performance of semi-supervised as they worked on supervised. So our aim is to investigate the performance of these prominent models under the semi-supervised approaches. These models are UNIT, attention unit, unit plus plus, double unit, multi-res unit, colon segment. So these are the merits of these models and the limitations of these models. And we also employ the res unit plus plus, min maxim, res unit plus plus models on 3 semi-supervised approaches. These are min-max similarity, which have the contrastive feature alignment and limitation of complex loss turning, and dual segment approach with the adversarial dual view learning with the limitation of stability issues, and deep co-training with the merit of same ensemble knowledge sharing with the limitation of computationally expensive. So our work is to combine the supervised with the unsupervised to make a semi-supervised learning in the domain of polyp segmentation for very reliable and uh, efficient segmentation without any dependency of annotation. Now come to the portion of our methodology. Here we have utilized two kind of data sets of polyp, which is KVC-SEG and CVC Clinic DB to perform our analysis. And this is the first approach of semi-supervised architecture, which is min-max similarity architecture. And here we use two models, and it is a contrastive learning based architecture. The core concept is to segmentation networks learn complementary special features through the contrastive learning, and loss component calculation is shown here to minimize distance between similar special features maximize for dissimilar regions. This is the critic based architecture, which is duo segment, and this architecture is to two segmentation networks complete the cooperate under the supervision of a critic network in a min-max game. The loss calculation from this architecture is also shown here. So now come to the um, architecture, which is called the deep co-training. This is a co-training based architecture. Here the teacher-student concept is utilized, and the core concept is multiple segmentation network teach each other via consonants on unlabeled data, maintaining diversity to prevent collapse. And the loss calculation procedure is also shown here for this architecture. And the training steps are also described in these points. So now come to the experimental details of our research. We have utilized four types of evaluation matrices in our analysis. These are DICE, IOU, precision, and recall. And the formulas are shown here with the purpose. DICE is used for overall segmentation quality. IOU is for strict overlap measure. Precision is for false alarm rate, and the recall for polyp detection rate. So this is our very interesting portion of our presentation. This is result and analysis. Here we have shown the analysis for two dataset, KVC-SEG and Clinic DB for the deep co-training algorithm. And here the UNet++ and USCoreNet, ColonSegNet got the most prominent result for this analysis, and our key observations are most stable framework across all models and levels and achieves robust generalization across dataset from KVC to Clinic DB. And the clinical insight is recommended as default semi-supervised strategy for reliable low annotation clinical segmentation systems. And these are the same analysis for the KVC-SEG and Clinic DB dataset for the duo segment algorithm, which is the critic-based architecture I have described earlier in our methodological section. And the clinical insight is useful for detailed localization tasks when trained models are stable, not recommended for broad deploying without tuning. And so this is the same analysis for the min-max similarity algorithm across the four evaluation matrices I have already described in the evaluation matrix section. And the clinical insight for the min-max similarity algorithm for these two datasets are ideal for high precision computer-aided diagnosis screening where false positives must be minimal. Now I'm in the end of our presentation, and to conclude our presentation, we can say that We have used 9 benchmark segmentation models under 3 semi-supervised approaches, and the best pairing identification is USCONET along with min-max similarity get the highest dice, and UNet++ with the deep code training architecture have the most balanced performance, and proper model framework alignment can shift accuracy by up to 30%. Only 20% level data achieves near supervised performance with 80% cost reduction, and clinical impact are very important. Enables reliable, low cost, high precision computer aided diagnosis for the colorectal cancer screening. So for our future work, we keep the combined active learning and temporal consistency to reduce the leveling by up to 70% and improve stability across video-based colonoscopy data. These are some references from our papers, and thank you so much.
Thank you, and well done, Numaya, for your great presentation. So now the floor is open. So any question for Numaya, please?
So, we have checked this fully supervised one if we use. So, what is the difference? How does it affect the result? In this case, do you have the problem of labeled data? So that's why you have semi-supervised one.
Thank you so much, Professor, for your kind question. Actually, label data are very much limited in nowadays for medical imaging, and there very much data hungriness in medical image segmentation domain and data scarcity also. So we thought that if we analyze the unlabeled data processes by the semi-supervised learning, it could be better for the future works.
So, have you changed the proportion of this level so that just get an idea how it is affecting the, if you change the little bit of, whatever data you have, level data you have, so if you change the proportion of that, and how does it affect the tendency, on this result? Have you checked that one, using this model?
Yes, sir. We have checked the performance of these prominent segmentation models, that how they acts on 5% level data, 20% level data, or 50% level data, so that we can predict that which model is more prominent in this section, and how much architectural developments we have need to more stable them, that so that they can work well in semi-supervised approaches.
What was the difference you found, when you go for 5% to 50% level data? What was the change in the result, or the accuracy of this? What was the percentage change in the accuracy?
Here we have shown the percentage changes of results for the level data, 5%, 20%, and 50%, and they're good in 50% and 20%, and for less level data and which is 5%, most of them have the less result.
Okay.
And for application, I have a question that did you talk to any clinic or diagnostic center or any doctors that you can apply this software?
Thank you so much, Professor, for your kind question. Actually, not yet. We have not talked with any diagnostic center or clinic or doctors about this.
No, how can you then, without doctors' participation, this is a very important issue, colonoscopy, and your research is going on without doctors or some health professionals who are working on diagnostic centers or colonoscopy, it would be a good choice, at least to consult at the beginning. You are doing output, you are having output only for the doctors, that they will decide, and patient especially. But you are proposing, but doctors is not involved, or a physician is not involved, or diagnostic center is not involved. That is where our researcher is having problem, I think. If you consider this in future, or at least
Yes, sir. Definitely, sir. You were right, sir. Actually, this project is now under our examination. So if we get the satisfactory result, then we will definitely consult with a doctor or clinical person to judge this implicancy.
No, it is also another thing that before completing it, you can always consult with them, because they are knowing these things very well, whether it is going to work or not. That is also good if you work with them before checking everything. I understand that will be involvement with the doctors or diagnosis center will make your knowledge more better and
Yes, sir.
insight.
Yes,
Thank you.
Numai. I think
Yes, sir.
I agree with the panel members. This is a very good suggestion, because it's really, it must be used by the doctors. Lots of
Yes, sir.
colonoscopies,
Definitely,
images,
sir.
and other things. So if you get some input from who are on the real world, then it will really more applicable. You understand that? So yeah, I understand that you take the data, you take the two source of data you mentioned there. So it's completely based on the data and images. But as panel members said, that if you have some conversation with who are really use your products or whatever you are doing, your research, it's always better to have some more insights, and it will shape your research in a right direction. All good. I think still you have
Yes.
time, and as you said, that still you are working on that. So in future, your team and other guys definitely you have the scope to integrated the inputs from the expert who are really using this.
Yes, sir. Definitely, sir. Sir,
colonoscopies and
actually,
data.
we have used the data from the established data set.
Yeah.
So these are also the well-known data set. These are used for polyp segmentation.
Yeah, we understand that. We agree with that.
Yes, sir.
That's not a problem.
Thank you so
But
much, sir.
Maybe in that case, may get the more level data and all this. That's why she's having problem with the level data and all this. So maybe if she interacts with the doctors and all this, maybe she will be able to get that.
Okay.
Thank you. Yes. Thank you, Numaya, for your nice presentation and nice answers. So our listed presenters already finished with these things. We have completed the listed presenter, but
Thank you, sir.
From the panel member, I understand that we have someone couldn't finish yesterday. So can we please, I'm asking, because I don't have the detail for him or her.
Aminul Sarkar.
Yeah, Aminul Sarkar.
Are
Can
you
you join?
there? Aminul Sarkar.
Hello, everyone.
Oh,
Good
send
afternoon.
me paper ID, please. Good afternoon.
My paper ID is 2025-236.
All right, so Aminul 2025-236. 2025-236. So Aminul, you can share your screen and bring your presentation, and that will be our last presentation for today, for this session. Thank you.
Can you share my...
Yes, we can see your screen. Just, yeah.
Okay.
Bring it to the presentation mode, please.
Hello, everyone. Good afternoon. Thanks for being here. I'm Aminul Sarkar. Now I am presenting our research, LightXNet, a lightweight deep learning approach for pneumonia detection. My paper ID is 2025-236.
Put it in the presentation mode. Start the presentation.
I'm sorry. Okay. Thanks, sir. Okay.
Go.
My co-authors are Mohammad Alamgir Kobir, Abu Zahid, Mohammad Jalaluddin, Tawhid Bhuya, and Atikur Rahman. Here is the outlines of my presentation. That is the introduction, problem statement, related work, research question, objective, outcomes, and impact, and then methodology, experimental result, conclusions, and future work, and then references. Here is the introduction. Pneumonia is the serious lungs infection mainly affecting children under 5 and older adults. It is a leading cause of death in low and middle income countries like Bangladesh. Early and accurate diagnostic is critical for saving lives. Chest X-rays are a common diagnostic tool, but manual diagnosis is time consuming and required more radiologist. Deep learning models can detect pneumonia automatically from chest X-ray, offering a high accuracy. However, most existing models are computationally heavy, making them difficult to use on edge devices, or their datasets are imbalanced. Here's the problem statements. Existing deep learning methods, dense net, rest net, efficient net, it is a show excellent accuracy, but they require high computational power, consume large memory, have slow inference speed. This issue limit real world deployment in low resource or mobile healthcare setups. There is a need for lightweight, fast and deployable deep learning model for pneumonia detection. To overcome these challenges, we propose LightXNet, a lightweight and efficient model for pneumonia detection that balance accuracy and resource uses. Here's the related work. Deep learning models such as CNN, ResNet, VGG16, DenseNet, and MobileNet have been widely used for pneumonia detection. Many models achieved high accuracy up to 99%, but often used a small or biased dataset. Were computationally expensive, lacked deployment feasibility on edge or mobile devices. Transfer learning and ensemble methods improved performance but increased complexity and inference time. Here is the some researchers use like Almaslaks et al. Use a hybrid model using DenseNet 1-to-1 plus DNN achieve 98.9% accuracy. But yeah, there is some limitation, that is they require large dataset, lacked cross validation and real world testing. That's why we use a LightXNet with optimized preprocessing for beta generalizations. Similarly, the other authors also, some are use ensemble learning, some are ShuffleNet, used VGG16, VGG19, ResNet. This ensemble increase the complexity and computational time, and the traditional machine learning combines limited scalability. Heavy models, high memory use and solo inference times is lack of this limitation. So we use a single lightweight model achieving balance between speed and accuracy. We use a fully deep learning based pipeline optimized for edge deployment. We designed a LightXNet with only 18.8 megabyte model size. Here is the research question. How can pneumonia be diagnosed quickly and reliably using deep learning even in low resource environments? Can a lightweight deep learning model achieve high accuracy in pneumonia detection while maintaining low computational cost? Can such lightweight AI models contribute to affordable real-time medical diagnosis in low-income or rural healthcare systems? These questions guide our exploration towards developing a deployable, efficient, and accurate AI-based pneumonia detection system for real-world healthcare setting. Our objective is that to develop a lightweight, efficient, and deployable deep learning model for accurate pneumonia detection using chest X-ray. Design a lightweight chain-based architecture that balances between accuracy and computational efficiency. Evaluate the proposed LightXNet model using a standard metrics like accuracy, precision, recall, F1 score, and compare it with the baseline model MobileNet V3 small and EfficientNet V0. Apply model quantization to reduce model size and RAM uses for deployment on edge and mobile devices. Our objective is to bridge the gap between high performance deep learning and real world deployability in medical imaging. Here is the outcome. So we get the high accuracy, get a lightweight model, fast inference time, efficient training, quantization benefits, real world applicability, scalable and affordable. We get highest accuracy, that is 91.35% test accuracy, and F1 score is 0.92. When we use quantization, then we reduce the model size from 211 megabyte to 38.4 megabyte. Here is the methodology. We use a public chest X-ray pneumonia dataset, which is split into three parts: train, test, and validation. For pre-processing, we use we resize the images, normalized, and then augmented with rotation, zoom, and shift. For training setup, we use Adam optimizer, and the model is trained up to 30 epochs with a base size 64, with a learning rate scheduling and early stopping. All models that is experimented, MobileNet V3, Small EfficientNet B0, and LightXNet, were trained using the same setup, ensuring fair and consistent comparison. Based on MobileNet V3 Small, we pretend ImageNet, we frozen the last 30 layers with fine-tuned so that we get the low-level features. We use a flattened with two dense layers, which is 32 and 16 units, with a base normalization, railway activation function, L2 regularization with 50% drop. In the output layer, we used activation function, that is a sigmoid, for binary classification. Here is the results of our proposed model. From MobileNet V3 Small, we get 92.15% accuracy, and our proposed model LightXNet achieved 91.35% accuracy. EfficientNet B0, which is 89.42, and when we used quantizes on EfficientNet B0, then we get a 79.42% accuracy. Here is the model comparison. Here you see that LightXNet achieved the lowest value from the all other things. That means it is deployable on the low resource areas, like the inference time. The MobileNet V3 Small achieved 5.370 seconds, and EfficientNet B0 achieved 8.200 seconds, while our LightXNet achieved only 5.01 seconds. For model size, MobileNet V3 achieved 91.52%, 52 megabyte. EfficientNet B0 achieved 211.50 megabyte, and LightXNet achieved only 18.78 megabyte. It is very less than the other models.
Yes, I will continue.
Aminur Sarkar.
Hello, sir. Sorry, electricity problem again.
You are in Bangladesh or you are in Qatar?
I'm from Bangladesh.
But your university is Qatar or which university?
I'm from Daffodil International University from Bangladesh, Dhaka.
Okay, okay. They are, I thought that, okay.
Okay, can I continue?
Okay.
Yeah.
Yeah, please, please. Okay, session chair is there. Yeah. Okay.
Yeah,
No
yeah,
problem.
continue,
Thank you,
continue,
sir.
please. But Aminul, please do not read all the data from the table. We can see it. So you are reading all the data from the table. You can just read 1-2 column, then we can see from like the table.
Okay, sir.
Yeah, you can start from here.
Discussion section. Since you know the light excited acid, 91.35% test accuracy, and F1 score is 0.92%, and the model size is 18.8 megabyte. Float 16 quantization successfully reduced model size of a heavier networks without large accuracy loss. Compared to MobileNet V3 and EfficientNet, LightXNet provides better trade-off between accuracy, speed, and memory uses. Here is the conclusion and future works. Enable real-world and affordable and deployable AI-driven pneumonia diagnosis for the resource income and rural area. Our light techniques is better than any other researchers. For future work, we extend the multi-class disease diagnosis, add the attention mechanism for better interpretability, evaluate model fairness across different dermoscopic groups. Here is the references list. And lastly, thank you, Daffodil International University School of IT, Washington University of Science and Technology for their supports, and the Division of Information and Computing Technology, College of Science and Engineering, Hamad bin Khalifa University, Doha, Qatar, for their valuable guidance. And finally, I appreciate my co-authors and the reviewers for their valuable contribution. Thank you, sir. Thank you, everyone.
Yeah, thank you very much, Aminul, for your presentation.
Thanks.
Yeah, I mean, we are in the very last stage. So from the panel, any question for Aminul, please?
See, there are certain, when you take this data, then there is, how we are, there could be some variation in the data because how the patient is positioning, themselves or some different equipment, they have taken the data. So, how did you figure out? Because then in the variability in the system would lead to some kind of, ambiguity when you were taking the data. So, how did you solve that problem? Or did you encounter this kind of problem?
Firstly, we use a data set that is publicly available and it is widely used in many research. Since the data set is imbalanced, we use the data augmentation system like rotation, horizontal shifting, vertical shifting. That is very useful for balancing the data set. I use in my research this data set.
And also, when you have these, different, say, lung problems like pneumonia, but it could be overlapped with certain other lung diseases. Okay, so there could be some overlapping. So you have to be very sure about the particular image you are taking, that is of pneumonia. Otherwise, so you have collected only those are marked as pneumonia, is supposed. But there could be some ambiguity there also. Some other type of lung diseases or some kind of chest problems could be, showing similar type of trends and all this, or have some overlap trend. So, did you encounter these kinds of problems?
Sorry, sir, I did not provide your question.
What I'm asking, say, similar symptoms or similar kind of problems, could be images could be for some overlap diseases, not exactly pneumonia, but some other chest diseases, they may show similar kind of images or some overlapped images like that. So whether you have encountered with these kinds of problems or whether you have taken measures of that. With particularly chest problems, it's same kind of, images.
I'm sorry, sir.
Okay,
I
okay,
can.
so okay, fine, it's fine.
All right.
Thank you,
Okay,
sir.
Aminul, thank you. I think you're a bit exhausted. All right. So yeah, thank you so much. So with this, this is that we are running on 5th International Conference on Trends in Electronics and Health Informatics. So we were doing the session as a deep learning and medical image analysis. So I think we are end of this session, and with the permission of this panel member and everyone. So shall I conclude now, or do you want to say anyone want to share anything?
No, that's fine. Thank you so much, and thank you for joining. I think in Australia it is night or something like that. Around.
Yeah, it's only 7 o'clock. Yeah, almost.
Yeah, we are in around 2 o'clock daytime, so Samarkand, and it's a good city, very beautiful city, historical city. So
Okay,
I
so
hope
I think
here we'll be organizing a big conference again.
Yeah, I want
So
to visit Samarkand. So it is in which exactly, in where? I mean,
it's Uzbekistan, it's Central Asia, Uzbekistan. It was
Okay, right.
a Soviet Union, but it is now a different independent.
Yeah, I think we can collaborate from the Australia as well. But
yes.
I was instructed by Shamim Kaisar, so I was ex-colleagues of Shamim Kaisar. So we can collaborate more. We can some research collaboration.
Yes, there will be collaboration, and I hope so. There will be more participants from Australia this time, next time, and many papers we will get. Next, we will be looking for a big conference. Europe, and many European countries will be.
By the way, may I know your name, full name? I mean,
I'm Professor Sajjad Hussain. I'm Professor Sajjad Hussain. So I've been in Russia also. So Moscow.
Okay. All right, that's fine, Professor Sajjad. It was really nice to meet with you guys and in this session, and it was really enjoyable session. Thank you very much. And with these things, I want to conclude this session as a session.
Till which year you were in Jahangirnagar University?
I was till 2022, I think. Then I moved to Australia as a research fellow. Then I promoted as a senior lecturer, and I moved to another university. Now I'm an associate professor in university.
Fantastic.
Yeah.
Thank you so much. Thank you for joining, and thank you, participant. It is a very wonderful, though we are a bit late due to the keynote speeches from different countries, especially from US. They are night, and it was a little bit late also. So altogether, it was a good session, and today's session, and I'm thankful to again session chair. He has taken all the pain and more than half an hour.
It was really nice session. Yeah, and Professor Sadda was really helpful. He wants to take all the pains and make everyone's life easy. That I understand. He has a person that he can capable to take risk of everything. And thank you, my panel members, for nice comments and other things. And thank you all the students who are participating today. And
thank you,
everyone. Thank you, and bye, everyone.
Okay, we are leaving. So.